Okay, good afternoon. I'd like to thank Professor Eckstein and the organizers for letting me speak, especially so because I feel like this is the perfect audience for me to present this kind of work to. Okay, so I think we all know Douglas-Rachford splitting, but let me just review. So we consider this monotone inclusion problem where we have maximal monotone operators A and B. The decision variable is x, and then x is lives within a finite dimensional space, Rd. Douglas-Rachford splitting, which I'm going to, from now on, refer to as DRS, elegantly solves this problem with this fixed point iteration. This was, well, despite the name, it was formalized by Lyons and Mercier in 1979. And DRS is amazing. It's very elegant, and it has provided great value to the optimization community. So given the success of DRS, we might ask these two questions. Question number one, are there other two-operator splittings that, aside from DRS? And question number two, can we generalize DRS to the three-operator setup? And as Professor Goldfarb has mentioned yesterday, this has been an open problem for a while, and even Lyons and Mercier themselves mentioned that the convergence seems difficult to prove in the case of three operators. And after all, if you think about it, identifying why a certain tool works and trying to generalize it is a common and often very fruitful exercise in mathematics. And today I'll tell you the answer. The answer is, for question number one, no, there are no other two-operator splittings aside from DRS. And the answer to question two is no, we can't do this for three operators. And let me explain. So let me first establish the rules of the game, because we first need to agree upon what counts as a generalization of DRS. We need to agree upon what constitutes a generalization. To do so, let's review some of the key properties, the key interesting properties that DRS has. So property number one, DRS, the fixed point iteration is constructed using scalar multiplication, addition, and resolvents. And let's call this property resolvent splitting, because it just uses resolvents. That's the splitting. Property number two, resolvent with respect to A, resolvent with respect to B is only used once each. So let's call this property frugal. Property number three, given any maximal monotone operator A and B, the only condition is that A and B are maximal monotone. The step size alpha can be any positive number. So the method DRS iteration converges unconditionally. So let's call this property unconditional convergence. Property number four, DRS does not enlarge the problem size. And here's what I mean precisely by that. The mapping, fixed point mapping, T, is from Rd to Rd, and where the original problem size is in R dimensions. Another way to understand this is to think of this as DRS does not make any copies of the original variable. Let's call this property no lifting. And this will be actually the essential property in this analysis. And OK, so these are the four key properties of DRS. And now let's look for generalizations of DRS that satisfy all four or some of the four properties. To give you context, let me review some of the known existing methods. So forward-backward splitting solves this monotone inclusion problem with this sort of iteration. Here we're applying the resolvent with respect to A. Here we're applying the forward operation with respect to B. So first of all, this method is not unconditionally convergent. It's conditionally convergent. And there are conditions on alpha and B in order for this to converge. And also, furthermore, it's just not a resolvent splitting. This is a forward evaluation. There's nothing wrong with not being a resolvent splitting, but it's just not what we're considering. Here's a PDHG, also known as Chambol-Pock. So this, again, solves the same monotone inclusion problem as DRS. And this is the iteration. Now, the thing about this method is that this one uses lifting, because the fixed point mapping maps from R2D to R2D. And that's a consequence of going to a primal dual formulation. Again, there's nothing wrong about that, but this is an arbitrary rule that I'm going to set for the purpose of this analysis. Here is a three-operator splitting method that I called Davis-Yin splitting because it was done by Dan McDavis and my supervisor, Wo Tao Yin. This splitting solves this 3 operators problem where we use the resolvents and we also use the 4 evaluation of C. This splitting is a splitting without lifting because this is a mapping from RD to RD. So this splitting uses no lifting, but it's not a resolvent splitting because we're using the forward evaluation of the operator C. And in fact, there are many other splitting methods, and most of these have been developed quite recently in the past decade. And all of these methods do not satisfy these 4 properties. For the primal dual methods, lifting is usually the thing that gets violated. So these splitting methods certainly have provided great value. And in fact, many of these splitting methods, among these large lists, many of them include DRS as a special case. And therefore, they are legitimately a generalization of DRS in that sense. But they do not satisfy these 4 stated properties of DRS. And therefore, in this specific sense, they are not the generalization that I am looking for. And by the way, the proximal point method, of course, first worked on by Martinet and Professor Rockefeller, satisfy these 4 properties. But proximal point method, well, DRS generalizes PPM, not the other way around. So PPM, proximal point method, doesn't count. So here's the goal. So I want to study generalizations of DRS and possibilities by looking at splitting methods that satisfy these 4 properties. And this is indeed these 4 properties. It is indeed a very arbitrary requirement. These other splittings are very useful, even though they don't comply with the 4 requirements. Nevertheless, setting these rules and limiting the class of methods that we study will allow us to make meaningful conclusions. It will allow us to characterize what is possible and what is not possible. OK, so let me now move on to the first part, where I establish that DRS is the unique 2-operator resolvent splitting. So let me make some definitions more formally. So this is the 2-operator splitting monotone inclusion problem. And I'm going to say a pair of functions t and s is a fixed point encoding if x star is a solution, if and only if there is a fixed point such that the solution mapping gives x star. So for notational simplicity, I will drop the dependency of t and s on a and b. And the operator t is the fixed point mapping. And I'm calling the function s the solution mapping. So in DRS, you have the zk iterates. So the the fixed point mapping t will map from zk to zk plus 1. But when you have zk for large k, then you would apply s, which is just the resolvent of b, and you would recover the approximate solution x. So s is will be just the resolvent of a or b. And I say TS is a resolvent splitting if the fixed point encoding is constructed with resolvents of A and B, addition, and scalar multiplication. So I can use scalar multiplication, addition, resolvents of A and B. That's the only thing I'm allowed to use, computationally speaking. I'd say TS is without lifting, does not use lifting if the mapping of T is from RD to RD. And I say TS is frugal if it uses the resolvents of A and B only once. I am allowed to use the resolvents with respect to different scaling parameters, but the resolvents I can only use once each. And the final definition, I need to define equivalent mappings. So let's say you have this fixed point iteration. You can multiply by a scalar in front and get essentially the same iteration. So I'm just going to say that's equivalent to the original thing. Also, when we have these 2 operators A and B, the problem is specified symmetrically. I have monotone operators A and B. So if I swap A and B, so here's AB, AB, BA, BA, I get a different iteration. So it's not the same iteration, but it's conceptually speaking, there's nothing new there. So I'm going to also call that equivalent. So 2 splittings are equivalent if you can obtain one from the other through scaling via scalars and swapping the order of A and B. OK? OK, let's get to the first theorem. So theorem. So up to equivalence, any frugal resolvent splitting without lifting for the 2-operator problem can be expressed in this way. So here I'm imposing the three conditions. Condition number 1 is frugal. Condition number 2 is the resolvent splitting. And condition number 3 is without lifting, so it maps from RD to RD. I am not imposing convergence. Convergence I'll talk about soon. If we impose these conditions, this is any resolvent and any such splitting will exactly have this form, where alpha and beta are positive quantities, theta is not equal to 0. OK, so this contains DRS as a special case, but it's more general than DRS. The fourth condition was convergence. So let's examine when this converges. Oh, by the way, I need to define the property. So I say the fixed point encoding converges unconditionally if it always converges. That's what this means. So for whatever monotone operator A and B, if this thing converges to a solution, that's unconditional convergence. OK, second theorem. So among those fixed resolvent splittings that I showed you in the previous theorem, only this one. OK, so this one converges only if alpha is equal to beta. And alpha equals to beta is exactly the case of DRS. Do you have a question?
Is alpha beta switch in the beta over alpha thing? Alpha over beta?
Maybe. I'm not quite sure. I'll check again.
That might fail fixed point encoding.
Right. If I made a mistake and swapped the order of alpha and beta, then it would not be a fixed point encoding. Yes. I'll make sure if this is correct after the talk. So anyhow, the theorem is perhaps a modulo some typo. This splitting converges if and only if unconditionally if it converges unconditionally if and only if we have DRS. So there were some additional splittings that we could have investigated, but when I investigate them, they don't all. The cases that are not DRS will diverge for some cases. And here's the proof. Here's a really quick proof. So I look at the particular monotone inclusion problem, where this is two-dimensional, and this is the operator A, this is the operator B. And when alpha is not equal to beta, the solution is unique at 0. When I run DRS, the fixed point mapping looks like this after some calculations. And the eigenvalue of this mapping is strictly bigger than 1. And therefore, when alpha is equal to beta, the iteration diverges. This means only beta equals alpha has a chance of being unconditionally convergent. And we all understand when DRS converges. OK, are there any questions so far?
You can have mixing factors other than a half, right?
Sure.
Convergence, but that's included under DRS. Right?
So you're saying that I could use a different theta for different iterations, right?
Yeah. Well, okay, just theta. Right?
Yes. So I'm implicitly assuming that I'm applying the same mapping every iteration.
But the theta is the overrealization.
Yes.
Because before, like 3 or 4 slides ago, it was just a half.
Right. Yeah. So to be precise, I probably should be saying relaxed Pieceman-Rachford splitting is the unique two-operator splitting.
Under relaxed.
Yes. Yeah.
Concerning the algorithm you mentioned from Patrick Combet, which algorithm are you thinking to?
Sorry, can you repeat?
Which algorithm do you refer when you talk about Combet algorithm?
The primal 2 or 4 back or 4.
Yeah.
Forward, backward,
Sorry.
forward.
The primal 2 or
This one, I think it's. I think this is the forward backward forward on the skew symmetric system. Yes.
And I'm thinking about Ogazo algorithm.
The what algorithm?
Ogazo algorithm.
That doesn't have a fixed map, though. Because you always have to go back to the start.
I'm not familiar with that algorithm, but I'm happy to talk offline.
But this is the only algorithms for the sound, for zeros and sound operators.
Yeah, but maybe in Ogazo you can speak also.
Okay.
That's what Patrick recently, we applied the splitting method with Ogazo, domain decomposition, it works.
But this is a primal 2 algorithm. KKT set.
primal dual.
Yeah.
But
Yeah,
also,
you're approaching the KKT set, the set of
Yeah.
and this is not allowed.
It's not
Yeah, so this one violates the lifting condition.
Another one, that you been mentioning, but it's another primal dual method, and then not allowed.
Right. So when you go to primal dual, immediately my rules will outlaw that because it's lifting. Now, of course, I'm not making any value judgment on lifting. It's just an interesting, I think, assumption. OK, I'll move on to the 3-operator setup. So let me just redefine a few things because just for clarity. OK, so here we have the 3-operator problem, A, B, and C. This is the definition of a fixed point encoding. And TNS, this is a resolvent splitting if we only use finitely many resolvents. So I don't know, maybe it's possible if you use infinitely many resolvents, but I'm going to rule out that possibility. And TS, this is without lifting if the mapping, fixed point iteration mapping, is from RD to RD. OK, let me state the impossibility result. There is no resolvent splitting without lifting for the 3-operator problem. And let me clarify the meaning of this theorem. So let's assume the mapping, fixed point mapping, is it's RD from RD. So this is without lifting, this is key. So we have this no lifting condition. And let's assume these mappings are constructed with finitely many resolvents. And so I can use as many resolvents as long as it's finite. And they can all have different scaling parameters. So the alphas, the betas, the gammas, they can all be different. And by the way, this theorem is not talking about convergence in any way. So what fails is the fixed point encoding. So such a mapping will fail to be a fixed point encoding for some monotone operator triplet A, B, and C. And to remind you, if a fixed point encoding means if you start at the solution, you stay at the solution. And that condition cannot be met for some operator A, B, and C under this assumption. To put it differently, so the set of operators constructed with resolvents, identity mapping, and scalar multiplication, this forms, I guess, a near ring. And no element of this near ring is a fixed point encoding for 3-operator. I've heard, for some people, this explanation seems to be more clear. I don't know.
So what's a near ring?
Near ring is like a ring, except that it is right. So the distribution, it's right distributive but not left distributive because the functions are not linear, so therefore the distributivity property doesn't hold. OK. All right. So now I'm going to talk about a third topic, which I think is a natural follow-up question to the second result. So let's go back to this 3-operator problem. If somebody asks me how do you solve this, well, of course we can solve this with DRS. We just employ the standard trick, just copy variables, threefold, and so we have this system, and we can apply DRS. So we can solve it. This is not a problem that we cannot solve. And if we apply DRS and spell out what the iteration looks like, it looks like this. So this mapping T is a resolvent splitting, because we only use resolvents. It's frugal. We only use JA, JB, JC once. And it's unconditionally convergent. But it uses lifting, because the mapping is from R3D to R3D. So we can solve this problem. And to solve this problem, we need to use lifting. I demonstrated that without lifting, we can't construct a fixed point encoding. But with lifting, we can do it. So then, if so, how much lifting do we need? So let me quantify the notion of lifting. So I'll say a resolvent lifting, a resolvent splitting uses L-fold lifting if we map from T from RLD to RLD. So this is a fixed point mapping, so it has to be mapped onto itself. And the solution mapping should take the iterate in LD to D, because RD is the original problem dimension. And under this definition, for clarification, one-fold lifting corresponds to no lifting. So we can obtain an unconditionally convergent minimal frugal resolvent splitting with threefold lifting. We cannot do it with one-fold lifting. Can we do this with twofold lifting? That's the follow-up question I wish to answer. And the answer is yes. We can achieve this with twofold lifting. And since one-fold lifting is impossible, as I've demonstrated, or as I've told you about, I'm going to call twofold lifting the minimal lifting. So this is the result that proves that point. So this operator, which maps from 2D to 2D, defined in this way, is unconditionally convergent for any positive alpha and theta between 0 and 1. How do I prove this? I prove this with based on first principles. So I have inequalities, firmly non-expansive inequalities. I use those things. And I prove it that way because, to the best of my knowledge, this splitting doesn't reduce to any existing splitting that I know of. Maybe it does. If you can identify it, please let me know. That will simplify the proof. But I don't know of a way to reduce this to known splitting methods. OK, so I just showed you a brand new splitting method. And whether the splitting is fast or efficient is kind of besides the point, because what I wanted to demonstrate was that this twofold lifting is a minimal lifting, and then that thing is attained. But there's no harm in trying this out. So let's just try it out and see if it's efficient or not efficient. So I'm going to apply this to this portfolio optimization problem. So I'm going to consider this a proximable term, which will mean I'll have to invert this matrix, but I'm willing to do that for this problem size. This is the projection. This is the simplex. This is some linear constraint. So I will skip the details. I run this with problem size n and d, relatively large. So I wouldn't call this a big data problem, but I'll call it a medium data problem because with this data size, with this dimension, the data is 2 gigabytes in size. So I think it's medium size. So yeah, this is it. So purple, that's DRS, and the purple is the result of running DRS with the variable copying threefold. So this purple is based on the known splitting.
Basically spin-guards method.
Yes, yes. And then these other ones are based off of these other ones are the new splitting with different theta parameters. So for theta equals 0.5, the method does better than DRS. For theta equals 1, convergence is not guaranteed, but somehow it does converge. But so if you don't want to accept this version because there was no guarantee of convergence, fine. But the red line was guaranteed to converge, and it actually did converge slightly, not significantly, though, faster than DRS. So it seems to be reasonable, at least. OK, so I'm pretty much done. So this work shows 3 things. The first question was whether DRS was unique or not. And it is unique. DRS is the unique, frugal, unconditionally convergent resolvent splitting without lifting for the 2-operator problem. Question number 2. For 3 operators, if you insist that we want a resolvent splitting, and if we insist that we are not going to use lifting, if we impose these 2 conditions, then 3-operator splitting is impossible. Question number 3. The resolvent splitting is sort of, the fact that we want to use resolvents is often not a choice. But whether we want to do lifting or not is a choice. So if we want to do lifting, and if we want to use a minimal amount of lifting, then twofold lifting is the minimal amount of lifting. And I demonstrate that by providing a splitting that attains that lifting. I haven't been able to explain the key ideas behind the proof, but I will try to do so in the next 30 seconds. So the idea, there are 2 steps to the theorems that I did not illustrate, the proofs that I did not illustrate. So part 1 is parametrizing the splitting and simplifying it based on a technique inspired by Gaussian elimination. So what I mean by parametrizing it is since the assumption is that the splitting is constructed with scalar multiplication, identity, and resolvents, you can pretty much have an explicit parametrization of your entire splitting. And it'll have for the 2-operator splitting, it will start out with 15 parameters, but you can get rid of them, eliminate them one at a time. So you do this careful elimination based off of ideas inspired by Gaussian elimination. And for the 3-operator case, I run into the situation where using Gaussian elimination, I cannot show what I want to show. The second stage of the proof is to show that because Gaussian elimination fails, I can construct a counterexample. And that's actually the more subtle, trickier part of the proof. And OK, and that's it. Thank you.